So the subject of this talk is going to be about Shiny, which is a Python data science web application framework, and in particular, kind of the details of how Shiny renders things, because that is a big part of like understanding that algorithm is a big part of understanding why Shiny is worth your time, and also how to use Shiny to best effect. So the main thing that I learned as a data scientist is that when you're building data science applications, you really need an application framework with range. What I mean by range is something that can handle very, very small problems as well as very, very big ones. And the reason for that is that data science projects in particular usually start small, but end complicated. So they start as a simple dashboard or a model, something to explain a model. But then as those things become more useful and more used by your organization, people add requirements and they grow in scope, right? And if you pick a framework that's limited, that handles the simple cases really well, but doesn't have the tools to build larger, more complicated apps in a performant and kind of easy to understand way, you're in for a lot of pain. And I've seen this a lot with people building simple sort of demos in one application framework and then needing to just throw the whole thing away and build it again in JavaScript halfway through the project. Those things can be really, really difficult. And so the question I would encourage you to sort of ask when you're thinking about this is, both does your framework solve the problems that you're facing right now, but also are they going to solve tomorrow's problems? Are they going to be able to handle the problems that come up in the future? And understanding the way that these frameworks work a little bit helps you kind of anticipate whether they're going to be able to do that. So Shiny is a new to Python framework. It has a long history in the R community, but the idea is that it's a framework for building fast, extensible web applications. A pure Python implementation was released about a year ago. And the core value proposition is that Shiny is easy enough for rapid prototyping, so you can build something in a couple of hours or a day, but it has everything that you need to build a full-featured product. So if your application does grow and become something that you, your team, or your company need to rely on for a long period of time, we have all of the tools that you need to build and maintain a performant large application. So let's just take a look at an example here. So this is an example with 3 tabs. So the first one is a model training dashboard. The second one's some monitoring, and the last one is data annotation. And so this kind of shows a little bit the growth of a data science web application. So maybe I build a little classification model, and I want to expose it to people to be able to show them like how that model performs on their particular account. So this maybe is something I would have a sales rep have open when they're talking to, Fritch and Fritch or whatever fictitious company they're selling to. And then I have the second selector that changes the metric plot that I'm using. You can imagine this having more options. So the 2 things I kind of want to point out about how Shiny works here, what Shiny is doing, is the first one is that when I change this account selector, since both of these plots rely on that account selector, they both update. But when I change this metric plot, only this one updates, right? So Shiny is minimally re-rendering components based on what needs to change, right? So when this training scores plot doesn't depend on this metric selector, so it's not changing. The second thing I want to point out, and I can't really show this to you, you just have to believe me, is that these background tabs are not rendering at all. So whatever is happening on these background tabs, until the user actually clicks on it, these are not calculated. So these are calculated live when the user is interacting with them. So I could have 100 or 100 tabs here, and that wouldn't really be a performance implication of how fast this application loads, because the background tabs aren't doing anything. And so those are that's the sort of performance or the efficiency of Shiny's framework, that it's able to do this. It's able to create these applications. So the question you might ask is like, okay, well, how would you do this, right? Like, how does this work? How would you sort of implement that? And one implementation, if you're familiar with Gradio, this is how kind of Gradio would implement something like this. And there's 2 kind of features of Gradio, and I think a lot of other Python web application frameworks. The first is that you have manual state management. So I'm sort of instantiating a state variable and manually like populating that, deciding when it gets updated, deciding when it gets changed, how it's initiated. And the second is that there's manual callback management. So I have this selector called account, And I'm saying like when I have this event handler that says like when account changes the selection, do this stuff, then do this stuff, then do this stuff. And I have another callback for when the metric changes. So do this, do this, do this, this. But when you look at the Shiny code, it's pretty different, right? So this is the total amount of code that Shiny is using to draw those two plots. And when you look at it, you sort of realize, well, hang on, there's no state management here, and there are no callback functions here, right? And that's a little confusing because like, how does Shiny know what to do if I'm not telling it what to do? Another way of putting this is to say we told Shiny what to do. We told them how to draw this score distribution plot, how to draw this metric plot, how to select which plot to pick. But we didn't tell Shiny when to do it, right? That's something that the programmer is not responsible for. And that's a little weird because usually in these frameworks, the programmer needs to kind of be in the weeds, doing like nitpicky changes about callbacks and state. How do other frameworks work? Well, so Streamlit has a pretty blunt but easy to understand execution method, which is just re-renders everything all the time. This is great because it means that you can take a script and turn it into a web application without needing to think too hard about it. But as your application grows, of course, rerunning everything becomes an increasingly large performance problem. And then most of the other ones, Dash, Gradio, Solera to some degree, use event handling. And what event handling or event-driven programming is just kind of what I showed you in that code snippet, which is you're manually defining the behavior which triggers a callback function. So you, the programmer, are responsible for that. And you, the programmer, have the opportunity to mess that up, right? So you have to do it is one of the problems with event-driven programming. It can be fairly easy to get wrong if you update state in the wrong order, or your callbacks functions fire incorrectly, or there's some kind of race condition, things like that. And it can be pretty hard to tell when you get it wrong. So my experience with event-driven programming is that when they fail, it fails by showing the wrong answer in the app rather than crashing or not showing anything. My favorite example of this is Slack. Periodically every month or so, I get this Slack activity notification that I cannot dismiss. It just stays there forever until somebody fixes the bug. And I have this suspicion that deep in the Slack kind of notification world, there's a mishandled callback that's going wrong. So a better way, you might think of your application as a directed graph, right? So graphs are great because we know from the graph structure exactly what needs to be rendered to keep it up to date. So in this case, if C changed, we would know we needed to update E, G, and I, but we wouldn't need to update B because it doesn't have a dependency on C, right? So this is a really appealing way of doing these kind of efficient re-executions, but it has its own problem, which is that you have to kind of define this graph structure, which can be just as hard as defining callbacks. So Shiny strategy is pretty special. What it does is it infers the relationships between components, uses those relationships to build a computation graph, and then uses that graph to minimally re-execute your application. And I would suggest that if somebody kind of like me comes and says like, hey, I'm doing some magic inference to minimally re-render something with a graph, you should be a little suspicious, right? You should say like, okay, prove it to me. Show me how this actually works so that I can trust it. And I think the two sort of key things about this working is that for this to work, this inference needs to be 100% accurate, right? So it's not good enough if we get this right 90% of the time, because that's kind of worse than doing nothing, right? It gives you like terrible bugs that you have to worry about. And then for this to be useful to you, you kind of have to understand that it's working or how it's working. You have to trust it, right? So if you come in to Shiny with the idea that you need to manually define all the callbacks, that maybe is going to cause you more trouble than it'll save. So one question is, how would we do this? And an answer that comes up a lot is you could maybe do static code analysis. So I could read this code and say like, okay, I have this thing called score distribution, and it's reading an input, so I could draw a link between those two. But that doesn't work because Shiny actually supports dynamic user interfaces. So for example, this is a little application that lets you add to-dos and complete these to-dos. And this is the state of this application at any given point depends on previous user actions. So it's not actually in the code. Like there's nowhere in the code that says there's two list components. There's a recipe for adding one of those when you click the button, right? So I can't really do static code analysis with dynamic user interfaces, and we really want dynamic user interfaces, so that wouldn't work. So instead, what Shiny does is something called runtime tracing. What runtime tracing is basically we watch what all the components ask for, what things they need to run their calculations, and we use those to keep track of relationships. And then those relationships we can then use to build our graph and trigger our perfect re-rendering. So let's just walk through a little bit of code to kind of walk through how what I mean by ask for, what components ask for. So the first thing that happens is the user opens up the application, they request this plot by it showing up. So they requested this plot because it's being viewed. That has an ID. That ID links back to a rendering function, which is triggered. When the rendering function runs, it asks for some other inputs, and these can be either static, like in this case, they could also be dynamically generated. And then we get the input, right? So that's the sort of asking for this component, the link of what Shiny is doing. And you can kind of think of this as a small graph by just an input to an output. I'm going to talk about inputs as squares and outputs as circles. So let's review this graph again. So we have this account slider, which is consumed by both of these plots. And then we have this metric slider, which is only consumed by one. And when Shiny opens up, it doesn't actually know anything about the relationships between these things. The only thing it knows is that there are 4 of them. There's 2 inputs and 2 outputs. And it goes and just tries to calculate the plot. So it calculates the metric plot first. And the metric plot needs is both the metric selector and the account selector. And we got our little metric plot. And the distribution plot only needs the account selector. It doesn't care about the metric selector. So since this is only asking for this one, we only draw that one line. And right there, we have our DAG. We have our reactive graph, and we can use that to do re-rendering. So when the account selector changes, it does what's called invalidate, which means just say you need to recalculate, you're no longer up to date. It invalidates the 2 plots because it just follows those lines down and says those 2 had a dependency last time this ran. And then we forget everything, forget all of the dependencies attached to an invalidated output, and we go ahead and calculate it again. So metric plot calculates, then distribution, and we're back to our same graph. If the metric selector changes, though, the only thing that is invalidated is the metric plot. And since the distribution plot was not invalidated, all of its upstream dependencies were the same, that means we don't need to recalculate it. So we just recalculate the metric plot, and we get the same output, right? So that's kind of like maybe seems a little bit overkill because this graph ends up the same every single time, but these graphs can actually change dynamically. So for example, I have this case here where I have a radio button, which allows me to select which slider is active. So this one, the slider 1 is active, but slider 2 is not changing anything. But if I change the radio button, now slider 2 is going to change it, and slider 1 is not going to do anything. Here's the code that is generating that text. So again, it's a rendering function, but it has this conditional, or it's if choice 1, if the choice is slider 1, do this one, otherwise do slider 2. And when I start up again, I have Shiny doesn't know the relationship between these things, just knows there are these 3 inputs, the buttons and the 2 sliders, and this text output. So when I try to calculate the text output, I'm going to go ask for buttons and then get slider 1. And if slider 2 changes, nothing is going to happen, right? Because what Shiny knows is that since you didn't ask for slider 2 last time, that means it doesn't affect the calculation that you came to. There's got to be some sort of early return, or it's just not consumed at all. So I can kind of ignore this input for this purpose. When slider 1 changes, the same thing happens. It's invalidated. We go back, get the buttons. Button says go fetch slider 1, and then we're back to our output. If the buttons change, so now it says point to slider 2, we have a different case. So in this case, since it's pointing to slider 2, it invalidates, so recalculates text, goes and gets the buttons. Button says go fetch slider 2. And then we have this new graph where slider 2 is active and slider 1 is not active. And this again kind of leads to this implicit efficiency of the framework because these types of changes are tracked minimally, right? So you end up with the accurate graph all the time, and that graph gives you more or less perfect re-rendering of your application. So the great thing about this approach is that this actually scales, right? So you can use very, very simple applications can run with reactivity, but you can also build complicated ones. And importantly, every single Shiny app, from very small ones to very, very large ones, uses the exact same mental model of how these applications work. Works for dynamic UIs. That's what creates that kind of laziness where background tabs are not calculated. And you know that if your application grows, you're not going to suddenly need to like switch from using like rerun everything to manual state management in Streamlit, or from using stateless callbacks in Dash to caching data in a Redis database to share them between things, right? Shiny, like it's just reactivity. There's nothing else that kind of happens. It's able to span the full range of data science problems. I just want to check the questions here real quick. So the question is this like Django and Flask? It's not really. So Django and Flask don't generate UI. They're mostly like for the backend part of the application. And there's usually like some other UI front end, usually JavaScript on front of it. So Shiny does both of them. So this application, there's no JavaScript that was written. This is all done in Python. There's a Python function that defines the cards, one that defines the plots. It's just 100% Python. Okay, so the last thing I want to talk about is reactive calculations. So so far we've been working with basically pretty shallow graphs, right? Like all of the inputs are directly consumed by a rendering function. This is not that exciting, right? Like if you think of that big graph that I showed you, that had a lot of nuance. There were like these intermediary nodes. It was deep, and that depth is what leads to actual like real efficiency gains. So we have a decorator called reactive calc, which creates calculations whose results can be used by other reactive calcs or other rendering functions. And this basically adds additional nodes, adds depth to our reactive graph. And this will become more clear with an example. So here's an example where I have this again is like this dashboard growing. So I have the training dashboard, and then the model, say, got put in production. And now I need to monitor it, right? And I still have this account selector, but what I want to do is I want to populate this from a database sample. So I want to be able to like select some dates and then take a sample between these dates. And in particular, I want this part to happen in the database. Like I want this to be a SQL query that queries the database for all the accounts. And I want this part up here to happen in memory because I want this switch to be really quick. So what do I want? So just to specify the 6 things that I'm demanding, because I'm a very demanding user. So I want to query the database to sample between dates. I want to then be able to filter that sample by account in memory. And I want to share that data between the 2 plotting functions. So I don't want to have 2 copies of the data floating around. I just want to use one. Now to get more difficult, I want to cache the results of 1 and 2. So when the account changes, I don't want to take a new sample. I want to retrieve the cached sample. And I want to retrieve a cached sample for each account filtered with these 2 plots. And I want to invalidate that cache only when the upstream inputs change. So I want that cache to go away whenever the dates or the sample changes. But I don't want to take like retrieve an old sample from cache. Every time the sampling changes, I want to take a new sample. And lastly, and importantly for me, I don't want to think or work very hard. I don't want to like worry about it. I just want Shiny to get this right all the time. And this is the things that I think Shiny does better than any other framework, and in particular these last 3. Like there's often ways of accomplishing some set of these, but the ones where you can do the first 5 with most of these other frameworks usually involve a lot of thinking and work, and that's something that I'm unwilling to accept. So reactive calculations are defined with a reactive calc decorator. And the idea is that it caches its value so that it's cheap to call repeatedly and adds a node to the reactive graph. So because it's in the reactive graph, we can use that to do cache management. So we can discard the cached value when the upstream parts of the graph changed, and we can notify the downstream things that its value has changed. So here's an example of this reactive calculation. So you see I have these reactive calc decorators that are just decorating a Python function. And then this is the render plot that would plot one of those score plots. So these can be stacked. So here I have this sample data function, which is then being called by filtered data. So this is basically like referring to that function. And then that filtered data is called by the plotting function there. So I'm going to represent these reactive calculations with these little hexagons. So again, when Shiny first launches, it doesn't know anything about this application. It just knows there's 2 plots, 3 inputs, and 2 reactive calculations. And so the first thing it does is it goes and tries to generate the model score plot. That model scores needs the filtered data frame. So it says, okay, I got to go get the account input and the sampled reactive calculation. And then when it tries to figure out what the sampled reactive calculation is, it says, oh, I've got to go get this dates and sample size. Right. So this is kind of the process of this scaling up in complexity, right? We've added some layers to it. You could imagine this getting much larger if we needed to, but it would still generate the correct graph. And when I do try to calculate the API response, I just go and get the cached value filtered, right? This hasn't changed. None of it's upstream. Nothing upstream of this has changed. So I can just retrieve the cached value and know that it's correct. And that means that these 2 plots are going to always share the same data. and they're never going to do more calculations than they need to. They're never going to take that filter twice. They're never going to take that sample twice. If the account changes, the filtered reactive calculation is invalidated. So it says, okay, you filtered invalidated, forget your dependencies, and also tell your downstream dependencies that they're invalidated, right? Because if you're wrong, then anything that depended on you is wrong. And so then the two plots get invalidated as well. And we do the same thing. We calculate the model scores, and we go get the account. But this time, we just take the cached value of sample, because again, the date and the sample size hasn't changed. So we can retrieve the cache. And API response does the same thing that it always does, which is just retrieve the cached value. When the sample size changes, though, everything is invalidated. This is kind of like a primary node, so everything downstream of it's going to change, going to invalidate. And it turns out that's all of the relationships. So then we're back to our starting place of recalculating the whole score. So model scores gets filtered, gets account, gets sample, gets these two other inputs, and then the API response calculates. Are there any questions about that or about anything that I've kind of covered so far? Okay, then very quickly, I'm going to go through effects. So this is the kind of like another stage of this getting more complicated, which like maybe I'm not satisfied with my model performance, so I want to like do some annotation, right? So I want to just like check that this is, you know, electronics or not electronics, and have this write back to a database. And so this interaction is really hard to think about with the tools that we've used so far, because I'm not really asking for the value. I'm asking to modify the state of a data frame. And so these would be called effects. So reactivity, I think it's a great default for these applications, but not everything fits it, right? Sometimes you do actually want to specify a side effect or specify that when something happens, right? So, you know, you want to batch inputs together, trigger a side effect. And event-driven programming, it's not like all bad. It's just, I think it's complicated when you use it as your only tool. So what we want is we want this annotation to happen when the user does something. So I want to specify when. And I don't want it to happen to react automatically to those inputs. So this is the code that does that. So we have these decorators, reactive effect and reactive event. So reactive effect basically marks it as an effect, which means that there's no return value that needs to get plugged into a reactive graph. It just kind of happens. And then it's almost always is paired with a reactive event, which basically just specifies when this particular input changes, fire the function. So this is really identical to like an on-change event listener in another framework. And then we have the content, which actually does the annotation. So reactive event can also be paired with a reactive calc or a rendering function if you want those to be, you want to override reactivity in those cases. And the way I think about this is it kind of like adds event-driven sprinkles or chocolate chips to a reactive cookie, right? So you want that to be like something that it's not your first tool that you go to. Mostly you want to use these reactive calculations because they'll tend to be more efficient and easier to do. But when you do need to kind of trigger a side effect or something, that's a good way of doing it. The overall rule of when to pick one or the other is about side effects and values. So reactive effect is for side effects. That's why it has effect in the name. This is like updating a database, deploying a model, writing a CSV, something that is like affecting the world outside of your application. And reactive calc or rendering functions is for values. So if I'm running a calculation or fetching data from a database or filtering a data frame, I'm doing something where I'm consuming the value within the application. Lastly, we have a lot of other patterns that as you kind of think about this and you think like, aha, that's a way that like DAGs are not going to work. Like if you have a cycle in your graph, you know, we actually have a lot of functions that handle most of those cases. If you find one that we don't handle, we'd love to hear about it. So some of the other things you should just be aware of is reactive isolate to prevent cycles in the graph. You can include data like a database or a flat file with reactive poll or reactive file reader. You could have parts of your graph re-render on a schedule with invalidate later. So that's basically having something where you're valid, but then just keep a timer for 5 seconds and then invalidate all of your downstream dependencies. And you can store things in variables with reactive value. So the summary, just to take away, is Shiny creates very performant apps with very little work. I think its algorithm is great, it's elegant, but it's not magic. You can actually understand and have an intuition about how this algorithm works. And your framework should be able to handle what your users want, right? So you should be able to have your framework grow with the things that your users want to do today, but also with what they want to do tomorrow. And it's a real shame to end up with a framework that limits you in terms of how you're able to respond to those requests. And that's all I've got here. So I have a couple minutes for questions if there's anything, but otherwise, thank you very much for your attention.